Continuing my introduction to surface metrology, today we'll be looking at roughness and how it's used. First off, what is roughness? Well, roughness is how much a surface deviates from its ideal form. A surface's ideal form is what it would look like had it never gone under any stress or strain. If a surface deviates heavily from its ideal form, it's considered rough and coarse. If not, and it only deviates a small amount, the surface is smooth. Lastly, wear produces roughness. Moving on to the effects of roughness. Roughness is a good predictor of performance. If a surface is more worn, it's not expected to be as effective. High roughness is equivalent to high friction and thus high wear. A rough surface has more surface area than a smooth one. This creates more friction and in turn more wear and tear. Reflection of light. Something to note is that smooth surfaces reflect light much better than their rough counterparts. And lastly, as mentioned earlier, rougher surfaces wear quicker. Now, let's dive into some things you might see in the lab. On the bottom in blue, we have a mock-up of a surface with a mean line through the middle. Now, starting from the top, we have RT, the maximum peak to valley distance. This is calculated by taking the highest peak and the lowest valley. And RZ, the average peak to valley height over several sampling lengths. This means we break the sample into many small lengths and take the average peaks of all of those. RP is the maximum peak height starting at the mean line and going all the way up to the highest mountain. RPM is essentially the same thing as RZ. RV is the same as RP, but starting at the mean line and going to the lowest valley. RVM takes the average valley depth over several sampled lengths. Average roughness is very important. It's basically how we tell how rough a surface is. This is calculated in two ways. First is the arithmetic average. It's used to calculate the surface's average distance away from the mean line, regardless of positive or negative. Root mean squared does the same job in a different way. Instead of using an absolute value to remove positive or negative values, it instead squares each value and then square roots it. These are known as RA and RQ respectively. Lastly, let's look at an example. Here we have a sine wave and a few values calculated. RT, the peak to valley value, along with the arithmetic average and root mean squared. I encourage you to try these out for yourselves, as they are good practice for the lab. Well, thank you all for watching. I hope you enjoyed. I've been Connor Cumming. Until next time.